So, good morning everyone. And last class we were seeing about probability. I gave you three videos to view. And there are five different areas we were discussing. And the last slide was about the conditional probability. So, in this class we are actually going to learn some application about that conditional probability. So that is why I asked you to view the video. So, already video content will take time to see the video. If you want more videos of this series, please ask. I can give you. But now you can put the attendance. നിങ്ങളുടെ പേരും നിങ്ങളുടെ roll number, maybe university roll register number you can write so that I can mark the attendance pass. So please type your register number and name on the live chat, like in the comment section. I think live chat is the best option, so you can type there. So I'm waiting for your attendance. Okay, thank you. So keep typing, type ചെയ്തുകൊണ്ടിരിക്കുക. Let us go into the class. So today we are going to see the topic likelihood functions. So this is a continuation of what we are learning, and this shows how we can detect the message signal from whatever we transmit. So we'll see the topic likelihood functions. So in this class I told you we are looking into likelihood functions, and it is based on conditional probability. We will see our block diagram that we saw in the first class of this module. We know that there is an information source is there. This is my source, and then I have the transmitter. So source, we have messages, so we wrote it as mi. Then the output of the transmitter, it will be suitably encoded into some waveform, so it is Si of t. Then it passes through the channel, and then it is received. So you have the receiver. Whatever we receive, we call it as x of t, and this is decoded and you get the information back. And we have already written x of t is actually equal to Si of t plus the noise W of t, and this is for the condition. Remember, time is varying between 0 and capital T, that is a pulse period, and I will be equal to 1, 2, etc. There will be m signals. So this is what we already learned, and so you can understand that depending upon the different message symbols, there will be different signals Si of t, and whatever we receive is called the observation vector. So that is actually a vector x, so it is the observation vector, and we are defining the conditional probability function. We write it as f. Since it is a vector, I am writing x. So this is actually bold x. It is a vector x, such that you receive x given mi. So you are transmitting the symbol mi and you are receiving x, and we are defining the conditional probability function. So what we do is now we will estimate what is mi. You receive x, and from that you estimate mi. So you find the estimate mi from whatever you receive. So this conditional probability function is what we call it as the likelihood function. And remember, likelihood function, we write it by L, the symbol L, and we write likelihood of mi. This is equal to the conditional probability. So mi is the, remember, input term, which is equal to the conditional probability function f subscript x given mi. But remember, x given mi is what we receive x on the assumption that we transmitted a particular symbol mi. So both of them are representing the same, they have the same equation, but their meaning are different. The likelihood of the message, we are writing the likelihood of message, but this conditional probability function is the condition that we receive x given we transmitted mi. And we have I varying from 1, 2, etc. up to m. Now what is this conditional probability density function? Let us see that expression. This is actually equal to 1 by square root of 2 pi sigma square. We know we have modeled it as a Gaussian random variable. So last class we also saw the expression for that. It is 1 by 2 pi sigma square exponential of x minus mu the whole square. So minus by 2 sigma square. And we know that we have calculated that also. Mean is equal to Sij. Sorry, mean is Sij, it is small s ij, and variance is what we write it as sigma square. This is equal to n0 by 2. So substituting that, what we get is f(x), so this is a vector x of x given mi is equal to 1 by square root of 2 pi into n0 by 2 into exponential of minus x minus mu I is Sij, the whole square by 2 sigma square n0 by 2. Bracket close. So this will give you the expression 1 by square root of pi n0 into exponential of minus, x minus Sij the whole square by n0. So this will be our conditional probability function, and this is for one particular message. We are transmitting one particular message mi, and what is the received vector x. So we know that we have mi where I varies from 1 to m. There are m symbols are there. So what we get is, we know that this is a set of Gaussian random variables, and this set of Gaussian random variables, we have that property what is the conditional probability density function? The conditional probability density function will be the product of the individual density function. So what I am writing is f x of x given mi. It is the observation vector completely given. This is equal to the product. So this is capital pi where I varies from 1 to n. It is f given. Okay, here we have xj where j varies from 1 to n because we can project it only on the n dimension. So this is, so what we get is, if we have complete terms now, it is 1 by square root of pi n0. It is a product of all the terms. So that is why I can write pi j equal 1 to n 1 by exponential of minus xj minus sij the whole square by n0. So I should take the product of these terms for j equal to 1, j equal to 2, j equal to 3, etc. up to n. Now we know pi n0 is a constant. It is not depending on any of these terms. So I can write it as this is equal to 1 by pi n0. This is actually a constant. It doesn't depend upon I or j. So I take the square root of that. So okay, I will have one more simplification. I write I write it as pi n0 the whole raised to minus 1 by 2. So square root of. Now there are n times it is multiplied. So it is n0 by 2. Okay. Into exponential of. See, you remember the term? അതിന്റെ product ആണ്. So it is exponential of a into exponential of b into exponential c like that. So it is exponential of a plus b plus c. So the product term becomes a summation term. Okay, and in every term you have minus xi minus sij the whole square by n0. So minus is common everywhere, n0 is common everywhere. So I take minus 1 by n0 outside and write summation j equal 1 to n xj minus sij the whole square. So this is the expression for the conditional probability function for the entire vector capital X given the symbol mi was transmitted. So this is the of the vector x given mi was transmitted. So it is for the entire vector. So even if we send mi, no, we might be receiving different types of signal because it get added with the noise. Our signal get added with the noise. So this is the entire probability density function. And here remember j varies from 1, 2, etc. up to n. I varies from 1, 2, etc. up to n. This is our condition probability density function. And it is better to work with when we have such a function. No, it is better to take the logarithm of likelihood function. So that we write it as L, small l of mi. So small l of mi is equal to logarithm of capital L of mi, where I varies from 1, 2, etc. up to n. So taking logarithm will be easy for doing implementation in digital signal processing functions. So let us see what is the logarithm. So we are taking the logarithm of this function. We are going to take the logarithm of this function. So L of mi is equal to logarithm of, we are going to take the entire thing, pi n0 whole raised to minus n0 by 2. Sorry, some of my letters are not visible. n0 by 2 into exponential of it is minus 1 by n0 into the summation j equal 1 to n xj minus sij the whole square. So I'm taking the logarithm of that. So what happens when you take the logarithm of that? You can take a log a plus log. There are two terms, no, pi and 0. So log a into b. So log into b, log a plus log b, something like that. So this one term is minus n0 by 2 into log of pi n0. And the other term is log of exponential of this term. So log of exponential of this term will be what? It will be minus 1 by n0 into summation j equal 1 to n. It is xj minus sij the whole square, where I equal to varies from 1 to etc. to n. So if you see the first term, it is actually a constant. So we will ignore this term because it doesn't have any relation to the message mi. So we are actually neglecting, and we are taking only the second part. So actual log likelihood function is our second part, L of m, which we say L of mi. This is our second part. It is minus 1 by n0 into summation j equal 1 to n xj minus sij the whole square, where I equal 1 2, etc. to n. And this function is used for the detection process. So this function is what we call it as the log likelihood function, and this will be this reduces our likelihood function to a series of additions. So it will be you can depending upon the symbol transmitted and the signal received, it will find the difference, square it, then for each of this message you can find it. So for each message signal there will be different possibilities. Our different possibilities are xj എന്ന് പറഞ്ഞിട്ടുണ്ട്. അതാണ് received vector in the components. And this is the function that we are going to use. So this is about the likelihood functions. Okay. And now we are going to see how we are going to use this likelihood functions to detect what is the symbol transmitted. So our next topic is the detection of signals in the presence of noise using this likelihood functions.